So yeah, today we'll be talking about machine learning and neural networks. So basically machine learning is a generalized term. The basic term is neural networks, and we'll come to that in a bit. So let's talk about machine learning in a bit. So what is the layout of machine learning? So basically uh, when we talk about machine learning, obviously, like I mentioned in the previous session, we want to make predictions using our program so that there is actually some sort of quote unquote learning happening. So we divide it into majorly three categories: supervised learning, reinforcement learning, and unsupervised learning. We will not be talking about reinforcement learning here at all. So that's why I haven't mentioned any subsections of it. But we will be talking about majorly about supervised learning. So supervised learning has two subsections: regression and classification. Regression is also known as statistical learning, which we have introduced in the previous session. So we'll be continuing with that, and then we'll do just a bit of touch up on classification. And then there is unsupervised learning, which covers topics such as clustering. There are many methods of clustering, and we'll talk about what clustering is in the last. After everything, there are only 2 to 3 slides on clustering, because our main focus of today's talk is statistical learning and regressions. So we'll be continuing with that. So yeah, in the previous session, we were able to establish a loss function, and we said that we need to minimize it so as to maximize our accuracy. So here, what I've done is we replace our regression coefficients with something known as weights, and we represent L as our loss function as a function of weights. Okay, so that's just a change of terminology. Okay, so there are lots of ways to minimize our loss function, but the one we'll be talking about in detail is gradient descent method. And we'll talk about what gradient is, and I'll give you the necessary information on it. So before going to gradients, let's start with a very basic example where our W, or regression weight / regression coefficient, belongs to real numbers. It is a one-dimensional case. Suppose our loss function is given as W square plus W minus 2, a simple polynomial function, and you are asked to minimize it. So minimizing it is quite easy. You just take its derivative and set it equal to 0, and you find the value of W for which it satisfies this equation, which is 0.5, negative 0.5. And you can check this indeed is the minimum of this function by using higher order derivative test. So if you take the second derivative, you see that it is a positive number, it is greater than 0, hence it is a minimum. So this is a basic example, and we will try to generalize it now. We will try to generalize it. Thus, we achieve a minimum of our loss function. So our basic idea is tweaking W such that it minimizes L of W, loss function. It's okay. So let's assume that W belongs to R square. So let's understand what R square is first. So R square is, well, R Cartesian product R. So R is an uncountably infinite set. It will be lots of ordered pairs, obviously uncountably infinite. It is basically a two-dimensional plane, right? So like I said, a vector can be represented by a column matrix. Let's say x is equals to y cap plus x equals to 2, 3. So this vector is modeled by two real numbers, 2 and 3. Thus, this is a very vague definition. It belongs to R2. This is a very big explanation of why it belongs to R2. So it has two entries. So if we have a three-dimensional vector, 2i plus 3j plus 4k, then x will be represented by 2, 3, and 4, belongs to R3, and thus we can generalize it to n dimensions. similar concept. So let's suppose our weight is belongs to R2, thus it is a vector, because we have assumed that every column matrix is a vector for our purposes. And this generalize, so basically what derivative is, a derivative gives you the, in at least in one single variable case, the slope of the curve, the slope of a curve, right? So we want to find the slope of a curve if W is a vector, if W is a two-dimensional vector. The gradient is a generalization of that for more than one dimension. So gradient of a function, of a multivariable function, I should say, is gives you the steepest ascent. Steepest ascent meaning the obviously maximum slope. It gives you the maximum slope. So it gives you the direction of steepest ascent. Direction of steepest ascent. Thus, we need to minimize our loss function. So we need the steepest descent. So we just multiply it by -1 and we get our steepest descent. So we take this is a symbol of gradient, okay? Take the gradient of our loss function and set it equal to 0, same process. But how do we actually take the gradient of loss function if our weight is a two-dimensional vector? This is how we do it. We take the partial derivative of each of its component. So bit on partial derivatives, let's suppose we have a multi variable function f of x comma y, x y plus x y plus y square partial f of x. So we take the derivative. So we treat y as a constant when we are taking derivative with respect to x. So treating y as a constant, this will give us y and this will be 0. Partial derivative with respect to y. We treat x as a constant. So this is x plus 2y. Okay. And let's do an example of what a gradient of a function is. So gradient of a function. So remember, gradient returns a vector value. Gradient returns you a vector. It gives you a vector. Hence, we say that we get the direction of the steepest ascent. The direction term implies that we get we get a vector value thing, and we multiply it by -1. So if a vector is in this direction, we get the gradient. We multiply it by -1 to get the steepest descent which we want. So this is a definition of a gradient. We are multiplied by unit vectors, of course, This is y I cap plus x plus 2y j cap. And as vectors can be represented by a matrix, so the gradient of f can be written as y x plus 2y. So this is the basic concept of how gradients and partial derivative work. And this is all you need to know for this session about them. There are some basic properties of gradients, algebraic properties, where here E are matrices, B is a column matrix. Okay, B is a column matrix. Column matrix. A is a n by n matrix. We won't be discussing proofs of these properties, but they will come in handy. You can use them. Just a thing to remember, these properties. Now we know that loss function can be written in this manner. We have just replaced beta with W's, if you remember from our last talk. This is just the expression which we derived in the previous talk, and now we just algebraically simplify it using some matrix algebra. If you remember it correctly, if you simplify it, you'll get expression something like this. It will take about 10 to 15 minutes. No, that's even more. 2 to 3 minutes, you can do it easily. And now this is sort of an exercise, or I shall say bonus exercise. This is not necessary when you're submitting your articles, but this is sort of bonus exercise. You are supposed to take the gradient of this and minimize it and obtain W star as this expression right here. And to do this, these properties, these three properties will be used, nothing more than that. So this is a bonus exercise. It is not hard, it is just a good exercise. It is a good way to do something on your own. It feels good. Okay, builds confidence. So a gradient, like I said, is given as this, and if you have a three-dimensional, if f depends on, let's say, z2 some z, then there's a k capital and so on, but where I've just written where f is a two-dimensional function. A gradient of a vector gives a rise over run or slope of the graph. So when we're talking, if f is a function of x, a single variable, derivative provides us slope easily, right? If f is a function of more than one variable, x, y, dot, 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 x or y, or let's say z, then gradient provides you with the slope, which is a vector quantity. It gives you the steepest ascent. Gradient gives you the steepest ascent. You can think of gradient descent method as, let's do it graphically. Yes. So let's suppose we have some function like this, okay, and we want to minimize it. This looks very complicated and stuff. So what we do is we start at some place and we calculate its gradient, and we multiply it by -1 to get the direction of steepest descent. Then we go to that place, we calculate the its gradient multiplied by -1, go there, and we do the same thing over and over until we reach its minimum. That is the basic concept. It's like a ball. If very easy example, we have a parabola. It's like a ball rolling down the hill where, let's suppose the ball doesn't know where to go. So in order to follow quote unquote laws of physics, it should be attracted towards this potential right here. It has some potential energy. It follows this downward direction, and this downward direction is given by gradient. This is a very vague but intuitive example, where it is also used in very quite widely in machine learning textbooks. So yeah. Okay, so we try to build a linear model, and we'll come to that, what a linear model is. First, we discuss some common terminologies. We come to features. These are the elements of the input vector. So if you have x as the input vector, the elements of this vector, let's say A, B, C. So these three are its features, or 1, 2, 3, or whatever, it can be anything. So the elements of this vector are called the features. The number of features is equal to the number of neurons in the input layer of neural network. So we are now starting to build neural networks. So the number of features, so let's x has 3 features, then there will be 3 neurons in the input layer of a neural network, in the first layer of a neural network. Then we come to weights. They represent quote unquote the strength of a connection between neurons, and they are basically our integration coefficients. Okay, the weights which we discussed previously. And then there are something known as biases. Biases are just simply constants. Biases are constants, simply constant, numeric value constants. And we'll discuss what are biases in detail after a bit. So basically, what we do is we compute what's known as a score. And score is a linear combination of feature and weights. So let's suppose we want to make a model of something that comes to my mind is, let's say we want to predict if this thing tastes good or not. Or so basically we just parameterize it by, let's say, two factors: how it looks and how it tastes. If it looks good, then you will try it. If it doesn't look good to you, you will not try it. So if it looks good, then how does it taste? So we have modeled this data by a vector with two elements. Okay. And we take each element, we multiply it. We'll call it H1 and H2. We'll multiply it by some weight, which we'll discuss. Weights are initialized, which weights are also numeric values. We'll multiply it by W1, W2. So the score will be H1 W1 plus H2 W2. That's all we are doing. And then hence you can generalize it to n dimensional, or any case where I have n elements in X and there will be n weights, then you can do that. It's quite easy. The basic example is this. You can always remember this to compute, to understand what score is. The score is the weighted linear combination of feature values and weights. It is a linear combination. Okay. But there are, so if it is a linear combination, it is a linear model. What we have made is a linear model for our neural networks. We have made a linear model. But there are, of course, limits to linearity. And the biggest drawback is we cannot define complex relationships between them. So let's say we have any complex relation, like any value between closed interval 0 to 5 is good, and over 8 is bad, and over 10 is worse. For any case, suppose in our previous model, if we get a value between 0 to 5, for it is considered good, and if it is over 8, it is bad. Higher than 10, it is worse. So we cannot define complex relationships using linear models. Thus, to resolve this, we go to non-linear models. Basically, non-linear model is, we take our score and we apply a function to it, a non-linear function, which is known as a non-linearity. We have computed our score W1, H1, W2, H2, and we apply a non-linearity, a non-linear function. And this function, this can be any function, any non-linear function. So F has many choices, such as sigmoid function, which is given like this. It is its mathematical form. And we have another choice, which is, this is called hyperbolic tangent of X, but don't worry about this. We won't be talking about this at all. We'll just be talking about sigmoid function. Okay. So let's talk about what neural network is. The neural network is, of course, made up of neurons like this. This is our input layer, and this is our output layer, right? Only one neuron has our output. And then we add what's known as a hidden layer between input layer and output layer, or it is also known as dense layers. So when we add hidden layers or dense layers to our neural network, it's not just a neural network, it becomes deep learning, or you can just call it at this point machine learning. So we have input layer, output layer, and if we add another dense layer for computation, it becomes machine learning or deep learning. And we connect each neuron by its with its previous neuron. Each neuron to its previous one. This to this and this to this and this. And these arrows represent weights. They represent weights or coefficients, regression coefficients. They represent weights. So this is a basic diagram. So yeah, these are our weights, 3.7, 2.9. I've just picked these values at random. This is not something that I've computed any model, just picking numbers at random and making a neural network. There is no meaningful prediction that you will get from this. By meaningful, I mean there is no just numbers and playing with numbers to help you understand it. There is no model for it. So simple neural network can be given as above, like this. So this is our input, output, and hidden layer. This tells us that there are our input vector has 3 elements. Hence, there are three neurons in our input layer. Be aware of that. So what we have done is we have a new innovation of what's known as a bias unit. So bias unit, we take no inputs, we just set it equal to 1. We take no input, just set it equal to 1. Like in this case, here we have taken 2 neurons as bias neurons. No input, just taken them as 1. And why we do that is because we have a linear model. So our output of each neuron, what happens, what the mathematics is, we compute the score, we add bias term to it. So this looks like, so this is a linear term, so it will be of the form m times x, or this is a constant. Bias is just a numeric number constant. It becomes y equals to mx plus c, an equation of line, straight line. So we have added c, so just so that it our model fits our data better. These are just constants which we add to make our model, make our model fit the data better. Okay. So how do we choose biases? Well, we just choose it at random. Use a random function, and we just through in each computation we just put sum equal to 1, and that is it. We just choose them at random. There is no need to focus on any particular. I chose these two. You could have taken these two or these two. It doesn't matter. Just you have to choose some bias units. And now let's see, how do we actually compute? How does a neural network actually compute a value? So let's perform the calculation of the hidden unit. So we will compute the value for this neuron, what this neuron gets, what value this neuron gets right here, what value this gets. This is 1, so we won't be worrying about this, but what value this and this change. So let's suppose we have our input vector is given by 1.0, 0.0, and we've chosen the third as a bias. So this is just a bias term. So our value of inputs are 1.0, 0, and this is our bias term. And then we have a hidden layer in 3 neuron hidden layer, and then there is our output. So what will be the value of this neuron? How do we compute what value will it get, and how does a neural network actually work? So what we do is, like we said, we compute the score, apply a non-linearity. Compute the score, apply a non-linearity. Of course, when we are doing it with a program and stuff, you don't have to do it by hand. This is just for understanding purposes. Then there are programs already written, or you can write from scratch for your own to do this. So basically, this is our score. So this is the value. This is our h. This is our h1 1.0. This is our weight 1. I've chosen weight at random too. Of course, everyone chooses weights at random. So this is our weight 1. This is our H2, weight 2, and this is our bias term times our weight. We've computed this, and then we've taken this as an input for our sigmoid function. Sigmoid function is defined by 1 plus e to the negative x. So if we compute this is very trivial mathematics. It will give you 2.2. You put it here, you use a calculator, of course, you will get 0.90. Then we similarly do this calculation for this neuron. To get the value for this neuron, we compute again the score H1, W1, H2, W2, and this is our bias term. We take it as an input for a nonlinear function. Here we have chosen it to be sigmoid. We calculate that, we get a number for the hidden layer neuron, and hence we follow this chain, and we see that the output the final output of this is 0.76. The output is 0.76. Let's suppose we have our output as 0.76. It's our final output. So let's suppose, and you must be thinking, how do we interpret these numbers? So let's say again the food example, we have modeled it by, let's say, any three parameters. It could be any three XYZ parameters, and we have said that if we get a value bigger than 0.8, we'll say that our food is tasty, it is delicious or whatever. If we get a value less than 8.0, we'll say it is bad or it is not worthy. That's how we interpret this. We are basically converting what we know into numeric values, mathematical numbers. So we can define these three parameters, which are real world parameters. Let's say texture, its smell or its taste, on a scale of 1 to 10. How good is it? It has a, let's say, 1. On a scale of 1 to 10, it has a smell of 1, it has a texture of 0, and it has a, I don't know, taste of 5 or 3 or whatever. So basically we convert these things into values. We put them in a vector, and then we make neural networks. As we have mentioned, how do we do that and how do we compute them? We compute the score, which is just the linear combination of these two. Then we take the score as an input for a nonlinear function, and we get the value for a neuron in hidden layer. Neuron, let's say, and then we do that for each neuron in input layer to get a value for neuron in hidden layer. Then we do that. Then we repeat the same process to get the output for output layer or output layer neuron. So of course, this is a very tedious process. It might be trivial, but it is tedious. That's why we use computers for obvious reasons. I mean, if you do this by hand, you're stupid, but this is just for understanding purposes. That's why I've done this with hand. Okay. So of course, there will be some errors. Let's suppose that this is a model. Let's suppose that technically that food item is a 1. And suppose that food item is a 1. It gets a final value of 1, and we are getting by some I don't know, some popular chef, they give it a 1 value from 0 to 1. They give it a maximum 1 value, and we're getting 0.76. So there is an error of 0.13 in our model. So how do we fix this error? Of course, in order for learning to happen, we need to fix errors. If we do not fix errors, there is no learning, right? So how do we fix this 0.13 error? Well, we use what's known as back propagation training. So let's suppose the output should have been 1.0 and we got 0.76, and so we have to adjust our weights accordingly. Again, we can only adjust weights. We cannot adjust our input data and or anything else. We can only adjust weights because biases are just constants. So you have to weights such that we get more accuracy. We go towards more and more accuracy, right? Obviously, we want a more accurate model. And one more fact about sigmoid function, if you guys must know, the range of this function is closed interval 0 to 1. So whatever output you will get it from 0 to 1, a closed interval. Okay, so be careful with that. It is 0 to 1. It has a range of closed interval. Let's talk about gradient descent again. So you obtain an error. Error is a weight of function. Error obtained is a function of weight. Sorry. And of course, we want to reduce the error. We use gradient descent and move towards the direction of minimum error. We talked about how we do that. We calculate the gradient, we multiply it by -1 to get the direction of steepest descent. Okay. And then we adjust the weights such that we move towards that minimum direction. So we've gotten that direction. Now we want to adjust our weights such that we move towards that direction. In order to move, we adjust our weights such that. And that's when back propagation comes in. So back propagation says it is basically an algorithm. First we adjust. So let me draw a neural network here. And let's suppose there are lines joining here. If I draw them, it will be confusing. So just imagine this neuron is connected to this, and you know the whole thing. So first we adjust the weights of the last layer. So this will have 3 weights. We adjust first these 3 weights, then we adjust these weights. So we go from last to first in adjusting weights to minimize our errors. We go from these weights to these weights. And if there were 2 hidden layers like this, then we will go to these weights. So we'll go from backwards to forwards. This is why the term back comes in from the back propagation, and we propagate error back to each previous layer. We propagate our error, we compute error, and we'll see that how do we compute error. We propagate it to previous layer, adjust our weights. So basically we are moving backwards to forwards, adjusting each weight. So now this is not just this weight, this is our adjusted weight, this is our adjusted weight, this is our adjusted weight. This is our new adjusted weight, adjusted weight, adjusted weight. So we're moving backwards to forwards, adjusting and updating our neural network to gain more and more accuracy. So how do we do that? So before going to that, let's discuss few things. So derivative, let's discuss derivative of sigmoid function. Sigmoid function is given by, you can take its derivative by quotient rule, and you can prove that its derivative is given by this. There is a simple one, the quotient rule you must all be familiar with. That quotient rule is enough to prove this. We can use quotient rule to prove this. So first we go to some terminologies. We denote score by S equals to this. Instead of writing score every time, we write S is equals to this. And we write our non-linearity, and we'll call our non-linearity from now on the activation function, because it activates our neuron, right? It gives it a value. We input score in our activation function, and it gives you the activated value of a neuron. Then we calculate L2 normalized error. So let's talk about L2 normalized error. So let's suppose T was the correct value, which is 1.0 in our case, and Y is the value that we got, which is 0.76. We calculate T minus Y is 0.13, and we basically calculate its mean square error. We are calculating mean square error. We're squaring it, dividing it by 2. We're basically calculating MSE. And if we have multiple output neurons, then we'll have a vector here. So that's why we say L2 normalized. Okay, we're basically taking the square, mean square. Now we want to compute derivative with respect, derivative of error, the change in our error term with respect to any weight wk. So we see that error does not depend on w. Error is not a function of w, but it is a function of y. Okay, so we use chain rule. We write dE by dy and dy by ds, because ys is our score, and then we write ds by dwk. Why are we doing that? And we have done that because we see that error is a function of y, so we can compute this derivative. We see that y is a function of s, so we can compute this derivative. And we see that s is a function of w here, so we can compute this derivative. And we have just used chain rule here, as you can see. So chain rule could be df by dx, where f is a function of df by dy, where f is a function of x. It could be written as df of x. We just use the chain rule here. We have used chain rule 2 times actually. We have used 2 times. And here we use the chain rule to write this thing. Right? We wrote it this way because we know that error is a function of w, this is a function of s, and this is a function of w. So we calculate each derivative individually. So dE with respect to dy would be derivative of this respect to y. This is quite trivial. You can see that this is negative t minus y. Dy ds, where sigma is a function of s, is sigma minus s into 1 minus sigma s. We proved that earlier about the derivative of sigmoid function. And dswj, where obviously h will be treated as a constant. So because it is a constant, so we'll just get hj. So we've computed all 3 derivatives. Now we just have to put them together to finally get the derivative or the change in our error with respect to our weight. And we get this. We put them together and we get this, where y prime denotes sigma s into 1 minus sigma s. Okay, this is a shorthand for this. Now we multiply it by a constant which is known as a learning rate. We can set it to be any value. Usually I have seen it to be 0.25, 0.5 or so. You can set it to be any value. So we have just multiplied this whole thing by a constant called eta, which is learning rate. Nothing else. We've computed derivative of error term with respect to w, multiplied it by constant. Sorry. Multiplied by a constant eta. That's all we have done. Great. So this is how we know how to adjust our weights. This is our delta w of j. So our change, how do we, what is the change term? How do we change our weights to get to the minimum, to get to the bottom of this hill? How do we change weights to get to the bottom of this? How do we change the weight so that this ball rolls down to the bottom of this hill, so that we minimize our error and maximize our accuracy? This is how we do it using back propagation. And just a FYI on multiple output neurons, we calculate error term. Let's suppose instead of having, we had a neural network like this, right? Only one output neuron. Let's have 2. So if you have 2, there must be some expected value of these 2. And suppose we get error of 0.13 here and 0.10 here. We just square each of each of these, and we add them, divided by 1 by 2, and we get our error for multiple neurons. And hence we calculate error term similarly for each multiple neuron. That's why there is a each output neuron. That's why there is a subscript k here. K represent neurons in the output layer. That's why I have a subscript k here and a factor of k here. So there is no factor of k. So yeah, that's why you get this value. That's when you get this value. For multiple out. This is for multiple output neural networks. Now let's talk about hidden layers or dense layers, whatever you call them. In dense layers, we don't have a specific output values. Dense layers are just sort of, you can see them as helping layers to get a desired value. They act as helper layers from so basically we want to go from input to output, of course, that's our basic intuition. But from going from input to output, we have some quote unquote helping layers, which we call as, dense layers or hidden layers. So we don't have any specific values for these dense layers because these are just helping layers. There is no desired output from each of them. They are helping to get the desired output. We are not expecting a desired output from them. They are just helpers. So we calculate error term in each node. So we forget our feature because they don't have features, of course. We just calculate the error term, this term right here, and then we back propagate it to the weights, and we get adjusted weights. So let's do an example. In that way it will be more clear. So we calculate the error. So we know that these are G neuron, right? So calculate error in this by eta times formula t minus y into y prime into h. Okay. This is 0.13. Let's suppose eta is 10. We do not take eta to be 10. Just to make my calculation easier, I'm taking eta to be 10. Y prime would be, you have to calculate the score for this value, 0.1676. We calculate that sigma of 0.76 into 1 minus 0.76. This is our error term. There is no h here. This is our error term right here. This is our error term. Then to adjust weights for, let's suppose, this dth neuron, we multiply it like this, eta t minus y value y prime, then h. We get a value for this for d. It will be something like 0.431 or something 438 or something like that. We'll get this, and then we subtracted this new value from our original weight value. Our original weight was 4.5. Subtract 4.38 and we'll get 4.891. This is our new weight. So we have updated the weight of this. We calculate the error. We calculate the error of the weight, and then we subtract it from our original weight. To get our new weight, and we do that for each neuron. We've done this for D, then we'll do this for E, for F, then we'll come to D, and then we'll do it for E, B, C, from E to A, B, C. We do this for each neuron. So that's what is happening when you will write the code of this. This is what will be happening in the background. let's talk about how do we initialize weights. If you remember, I said now I've chosen weights to be 3.7, 2.9 or something here, or 4.5 here. So how do we actually initialize weights? Well, there are lots of ways to initialize weights. The one way is you can just put any, you can choose any random value between any small. We obviously want weights to be small numbers. Okay, we want weights to be small numbers. So any value between this closed interval. This is a very basic method. No one generally uses it. A better way is for shallow neural networks with no dense layers. We initialize weight in this given interval, where k is the size of previous layer. So how many neurons? Suppose we have 3 neurons. We use it using this. And for deep neural networks, which have dense layers, we use this formula to initialize weights. The k is the size of previous. So for R, it will be this. Be -1 to 1. For us, this is our, according to this formula. There are, of course, many other quote unquote formulas or ways to initialize weights, but these are the very basic ones. I think you should know them. Of course, if you're using libraries like TensorFlow in Python, you don't have to initialize them by writing formulas on your own. They just do it on their own. You just have to use some sort of command and they initialize the weights and biases for you. So let's summarize our neural networks through supervised learning, through regression. So we have our neural network like this. The number of neurons in our input layer is a number of elements of our input vector. So if x, let's continue the example of our last time we had. How many tips the waiter will get. So let's suppose we have 3 values, 10, 20, 30. 10 will be 10, 20, 30. And we have to predict how on 7th day what tip the waiter will get. So we have our computation 0.76, or we have to say if the waiter will get 40 rupees tip on 7th day or not. So we decided by let's say if the value is greater than 0.5, then we say yes. If the value is less than 0.5, we say no. Okay. Then every neuron in the following layer is connected to the neuron in the previous layer. So this and so on there. So you just connected through them through weights, and then we choose some neurons to be biases. Obviously, they play the role of biases. No input, just we take the value as 1. We have chosen these 2, and then obviously we initialize weights. So then we initialize weights. We have chosen these as the weights. Okay. Then we compute the score. After computing the score, we apply a non-linearity, a non-linear function. We get the value for our hidden neurons, and then we do this till we get to the output neuron. Then we check what is the error. Let's suppose it was supposed to be 1.0 and we got 0.76. We calculate error. Error would be 0.13 whole square divided by 2, right? Then we calculate, and then we have to change weights such that, so we have to change weights such that minimizes errors, or so that the ball rolls down the hill. Remember, we have to choose weights such that the ball rolls down the hill. Simple. In order to do that, we need to calculate dE with respect to dwk, our weight. So calculate dE with respect to dy, because we know that E is a function of y, right? Just using logic, and y is a function of s, so we can calculate this, and s is a function of w, so we can calculate this. And hence, by using chain rule, we will calculate this by calculating each of these derivatives. Once we have calculated this for a single neuron, let's say this gth neuron, once we've calculated this for a gth neuron, we change the weights for, so G and D neurons are connected by this weight, right? So how do we change the weight for this dth neuron, which is connected to gth neuron? We use our algorithm e minus y prime w, and we get a value 0 point something, 4 point, I guess 431 or 8 we got, and then we subtract it from our original weight to get our new weight. So all of, when you'll do practical or in the lab, you'll see all of this is happening in the background. And if you use Yellow Submarine or Python, all of this and actually even more is happening in the background. This is the logic of what is happening when you want to do machine learning or neural networks. So basically we have, I'll just write it one more time so that you guys sort of learn it. Algorithm. Input layer, number of neurons in input layer equals to number of elements of our X input vector. Then we calculate the score, apply non-linearity to score. Then we get an output. Then we use back propagation. We calculate dE by dwk. Calculate error for each neuron, each weight neuron. Then we subtract error from each subtract it from the original weight value. Let's say this is our error to get the new, and then we do this again and again and again until we get good amount of accuracy. Let's say 94, 95 at least. There is a lot of going on here, because, well, yes, it is complex, but yeah, that's how it does it. We talk about classification neural networks. So in classification neural networks, you don't need to worry about them a lot. We won't be talking about any of the things in detail now. We have a predict class. Let's suppose we want to classify if this is a cat or a dog, right? The computer doesn't know, program doesn't know. We have to teach it. We have to learn it how to classify a cat from a dog. So in this case, we obtain a one hotkey type output, which is we get one any one of them and 0 for rest of them. This is known as one hotkey. One hotkey meaning we have 1 for a single neuron and 0 for other. So we have cat, dog, and another thing, bird. So if it is a cat, if this is a dog, this will be 0, 1, 0, 0, one hotkey type output. And yeah, you don't need to worry about probability distributions right now. So we'll talk about unsupervised learning. So in unsupervised learning, we use what's known as grouping. So if this is our data points, they're scattered like this. We cannot make a single line to predict their value because it just won't be enough. And let's suppose we want to predict where this lies. If this is a part of this group, or this group. We don't know if it is a cat, dog, or a bird. A computer doesn't know. So what we see is, okay, if it is here, it is near to these points in our data set. So it must be this. So we try to find out which group it is near to, which is known as k nearest neighbor. How many k is a number, how many nearest neighbors it has. When you are going to classify, you find its k nearest neighbors from our training set. Okay. And then we say, okay, this belongs to this group. So basic algorithm is, given a query instance to be classified, let's say XA, and we have k instances in total. And we have to find out where. Here is an example. So there are 3 clusters, right? 1, 2, and 3. And this is our query right here. So what we do is we calculate the Euclidean distance, which is given by this formula. It's a simple distance that we calculate in mathematics in a graph or whatever. Euclidean distance. And we see our query is near to which of these groups, and whichever is the closest to it, the number, we see that it belongs to that group, and that's how we classify using unsupervised learning. So basically we use unsupervised learning for mainly classification. We won't be discussing weighted k nearest neighbor algorithm. If anyone is interested, I'll share the slides and you can ask me about this algorithm. I will explain it. But I think this should be enough for this talk. I think I've already covered a lot and there is a lot for you guys to chew on. So if you think you have any doubts, you can obviously ask me right now or after the class.